moment, I will be discussing about the Laboratory Activity 10, FIR filters. So the objectives are to design and implement filters using Python, apply the FIR filter to a signal and visual effect, analyze the filter's frequency response. So let's code it. So here, first I've defined the or imported the PSNP, imported the matplotlib, the pyplot, the scipy signal, and the scipy FFT. So what happened here is that I've defined the parameters first for the sampling frequency in hertz. It's 1000, and for the time is NPR range 0, 1 over f of s. Okay, so 1 over f of s is equal to time. So this is the time vector for 1 second. So next is that I've generated two sinusoids, the low frequency 50 Hz and the high frequency 200 Hz. So there's here, this creates a sinusoidal waves and generate the low and the high frequencies. And then these two were added to create a noise signal. So the low frequency plus high frequency plus 0.3 times n per random. So this represents the actual noise in the surroundings. So next is that I've plotted all of this in a figure with the title of course and the labels and grade and legend. And finally to show it. So next is that for the filter specifications. So it has been defined the cutoff frequency, which is 100, and the number of tops, which is 51. So the 51 here is the number of filter coefficients. So since this is a low pass filter, frequencies below 100 Hz will pass through, while higher frequency will be attenuated. So next, to design the FIR filter using the window method or the Hamming window. So we have the FIR coefficients equal to Fir number of tops, comma cutoff is equal to cutoff frequency, f s is equal to f of s. So this is to provide a stable, and the Hamming window was meant to provide a stable and linear phased filter, ideal for signal processing. So next is the number of frequency response of the filter, and we have here the frequency and plot it. So next is to apply the FIR filter to the noisy signals. So it has been defined, the filtered signal is equal to the filter, and next is to plot the original and filtered signal. So after filtering, here we have the noisy signal to compute the FFT of the noisy filter signals. So after filtering this, the 200 Hz component and are significantly reduced, while the 50 Hz component is remaining. So, and of course, the signals have been plotted here in the show. So now let's start debugging. So as you can see here, this is the combination of low and high frequencies with the noise. And this is the frequency response of FIR filter. And here's the comparison of the noisy signal and with the filtered signal passed into the low pass FIR filter. And here's the magnitude spectrum of noisy signal and the magnitude spectrum of filtered signal. So that's all for this video. Thank you.